this is just a standard RC circuit. So if I was to try and write a Kirchhoff's loop through that circuit, then that Kirchhoff's loop would have E minus the voltage drop across the capacitor minus the voltage drop across the resistor equals 0. This is where you would have to start if you were asked to determine a differential equation that could be used to calculate the charge on the capacitor as a function of time. That gives us everything else. So we start here with the understanding that voltage across a capacitor is defined as the charge over the capacitance, and that the voltage across a resistor is defined as the current times the resistance. Ohm's law and the definition of capacitance make a feature here. So already 3 points, right? And you bring these things together to create your differential equation. Changing the capital Q to a lowercase q to recognize that we're looking at Q that is fluctuating with respect to time. We get here. And then one final substitution, the knowledge that we can define current by its derivative. And we now have a differential equation. Now what we do here is procedural. So solving the differential equation is a lot less about an RC circuit as it is about a procedure. We'd get almost the exact same equation if we had an object that was falling through a resistive medium and we were looking for the velocity as a function of time. They have the same shape. It seems relevant to ask you guys if you think there's something about nature that these things all tend to look the same. And I think the answer is yes, and you should probably consider pursuing that if you're at all interested in science. The procedure is for you to split the derivative, and that means to isolate the derivative and then split it into 2 parts. So that part doesn't take long. So the real question is, would you have time on the exam to do the set of steps we're going to have to do here? Because the next thing is to multiply both sides by dt. And then we have to collect the terms to be the same on each side, collect like terms. So anything with q has to be on the side with dq, and anything with t has to be on the side with dt. And that leads us to dt all by itself and r over e minus q over c dq. So that's the part of the process that isn't taught to you in calc so much, but it's the process that we use to get to a point where your calculus can actually be used, which is for R to take the integral of both sides, setting our limits based on the information presented in the problem, and that there was no charge on the capacitor at time equals 0. And we're searching for how much charge there will be on the capacitor at some future point in time. The left side of this is straightforward. You're going to get T. The right side, well, there is no straightforward antiderivative that we can use here. We have to use probably U sub. We can take the R out, sure, but that doesn't really clean this up. So let's do the U substitution, which means U equals something like that. And we'll say du dq equals, well, just negative 1 over c. So solve this for dq. And now we can sub back in. And so I'll get negative rc out front, the integral, leaving my limits off, of 1 over u du. I know that in your calc class you're doing it a little different, but because ours are future loaded, I tend to leave the limits off and put them back in after I take the antiderivative. So negative rc, natural log of u, evaluated now. I'll put my limits in after I put my sub back in. So I'm going to sub back in EMF minus Q over C, evaluated from 0 to Q. All right, so calculus has been done. What's left? Algebra, and a lot of it. So get that RC out of the way. Natural log of E minus Q over C minus natural log of E. I can bring those things together. So this gets me to a point where I can try and tease out Q. That's what we're trying to do here, is to get Q by itself. So raise both sides to a base E. Multiply by the denominator. I mean, I know this is a lot of work, and it comes right back down to how much time would you actually have to be able to do this on the exam? I don't really know. So I'm close to the end here. A little bit of algebra. There we go. This term, not a surprise. Remember, full charge is going to be total voltage divided by, or total voltage times the charge. That's implied in our definition of capacitance. So we do have the total charge making an appearance here. And you guys should remember, if I divide both sides by C, I'll get the voltage across the capacitor. If I divide both sides by R, I'll get the current in the circuit. And if I want the voltage across the resistor, well, there's a way to get that too. I just go back to my original function. 7 minutes, 33 seconds. Now that assumes that you have to talk it out and do all of these steps. I don't know that you have that kind of time, but that's what we're talking about if you're asked to show what the charge and capacitor is in a standard RC circuit. It's a lot just to get to the point where we have these guys. All right? I want to focus on these guys for a minute. So I made a mistake. It was because I'm in a hurry. And the mistake was made in service to generating these three. I just was in a hurry and didn't do what I should have done. So this says that the charge starts at 0 at time 0 and increases to a maximum. This says the voltage across the capacitor starts at 0 at time 0 and increases to a maximum. This says the current in the circuit starts at 0 and increases to a maximum. Which one of those can't be true?
Current one.
The current one. What did we do wrong?
Current decays.
I know that. That doesn't answer my question, but at least you are reinforcing why this is wrong.
You have to take the derivative.
That's right. I just thought, hey, I got voltage. I'll just divide by resistance. No, you got to take the derivative. That's right. If I wanted to find the current, I was supposed to take the derivative of this one. So in my zeal to be in a hurry, I didn't. You should do that. You should take the derivative. I am not going to spend the kind of time to take the derivative, but you should take the derivative. So you get voltage over R. The 1 disappears, though, and you just get e to the minus t over RC. So at time 0, we get maximum current, and after a long period of time, we get no current. So that's better.